Let's talk about semidirect products. So suppose you have a group G and it has a normal subgroup N and another subgroup K with the following property, that every element of G can be expressed uniquely as G equals N times K for some N in N and K in K. This is exactly the situation that we had in the dihedral group. So in that case, G was the dihedral group Dn. It had a normal subgroup of rotations which was isomorphic to Z mod Nz, and then there was this group K of order 2 which consisted of the identity element and one reflection which we called S. Okay, so then what you can do is you look at the elements of the form K n K inverse for any N in N and K in K. Now because capital N is a normal subgroup of G, this thing belongs to N. Okay, so let's write, this is some other element N prime, right? Let's write K dot N for K and K inverse. Then this is an action of K on N. It's an action of K on the set N, but it's not just an action on the set, it is also an action such that K dot N1 N2, well, what is that? That is K N1 N2 K inverse, but we can write that as K N1 K inverse K N2 K inverse, just because this K inverse cancels off with this K. So this is K dot N1 times K dot N2. Okay, so these are the features that we get when we have a group and a normal subgroup and this kind of unique factorization of elements. Okay, so the group structure. So now we know that the elements of G can be written as N times K. Can we write down the group structure on G in terms of the group structure on N, the group structure on K, and this action of K on N? So the group structure, group operation in G, how does it look in terms of this data? So if you look at N1 K1, I have an element N1 K1 and another element N2 K2. What I want to do is I want to try to express this product in terms of the group structures of N and K and of the group action of K on N. But see, we can write this as N1 K1 N2 K1 inverse, and then we can write K1 K2. Now here that's just because this K1 k1 inverse k1, this cancels out, so this have nearly not changed anything here. Of course, I'm using associativity all the time. Now look at this. This element k1 n2 k1 inverse, what is that? That's n1 times k1 dot n2 times k1 k2. So now this is an element of n, this is an element of k. So we've expressed a product of two elements written in the form n1 n times k, again in the form n times k. Now what we can do is we can turn these observations around to give a new way of constructing groups, and these are called abstract semidirect products. So in this, let's just start with, now we don't have a group G to start with, what we have is two groups N and K groups. Okay, what's more, we have an action of K on N, and this action satisfies the condition that K dot n1 n2 is K dot n1 times K dot n2. In other words, this action preserves the group structure of N. So it just doesn't just act on N as a set, but acts on N as a group. Now define a group. G equals n semidirect product K. This is called the abstract semidirect product of N and K by setting as a set G is just the Cartesian product of N and K, and group law given by n1 k1 multiplied by n2 k2 is equal to n1 times k1 dot n2 and k1 k2. Then it is easy to check that this group law makes G a group. So you can easily check associativity, identity, and inverse. Let's look at the dihedral group example. We can turn it again on its backwards, and we can say start with n equals z mod nz, k equals z mod 2z, which I will write as identity. I'll write it as 1 comma s. So this 1 is the identity of z mod 2z. Usually we write it as 0 in additive notation. Well, let's call it identity comma s. Okay, and this s is the non-trivial element of z mod 2z. And then define the action of k on n given by s dot I is n minus I for all I in z mod nz. Okay, and of course identity dot I is just I. That's part of being a group action. Then dn is isomorphic to the abstract semidirect product and semidirect product K. So this, we don't get anything new, we get back the dihedral group that we looked at earlier. But you can just tweak this a little bit to get new and interesting groups. So let's look at a new example. If instead of Z mod NZ, we start with n equals Z, the group of integers, K equals as before Z mod 2Z, which I'll think of as identity comma S, and I write S dot I to be minus I for all I in Z. Then you can construct another group which we'll call the infinite dihedral group. The infinite dihedral group is defined to be Z semidirect product Z mod 2Z. Okay, just by analogy, this Z is like, Z mod NZ as n goes to infinity, just, in some informal sense. And so this is called the infinite dihedral group. And this group has another interesting, it arises in another interesting way. Consider the graph L, graph with vertex set Z and edges of the form I comma I plus 1 for each I in Z. So visually this is just the graph whose vertices are integers 0, 1, 2, 3, dot dot dot, and minus 1, minus 2, minus 3, dot dot dot, and we join adjacent integers by edges. And I'll let you think about this. D infinity is isomorphic to automorphism group of this graph L. So I'll give you a hint here. Z acts by translations, and S is the homomorphism which takes the vertex I to minus I. We'll look at this in more detail in the exercises.